G'day, in previous videos, we started to look at describing waves from both quantitative and qualitative perspectives. Today, we're going to go a little bit further, and rather than just look at the wave form and its characteristics, we're also going to be focusing on the behavior of waves, what they can actually do when they're interacting with the rest of their surroundings. So today, we're looking at syllabus dot point 3.2.1 and 2, still in the module 3, waves and thermodynamics, focusing now on inquiry question 2, which is how do waves behave. So when we're looking at the behavior of waves today, we're going to be focusing on a handful of phenomena, including reflection, refraction, diffraction, and wave superposition. Some of these, at least, you should have covered in junior years, but today we're going to be taking a lot of these concepts a lot further, and in some cases, introducing some quantitative relationships. The other dot point that we're focusing on today is looking at the difference between progressive and standing waves. The third dot point in this inquiry question, based on resonance, is a concept which we're going to unpack in its own video. So we have a fair number of learning intentions today to introduce a bunch of different wave behaviors. The first one we're going to look at is reflection, and look at how waves can be reflected on surfaces of differing shapes. Also going to look at refraction and look at how waves can change their behavior as they move through different mediums. We're also going to look briefly at diffraction, as well as wave superposition. And this all has to do with how waves can interfere with each other. We're going to be explaining how that works. And at the end, we'll have a look at distinguishing between progressive, also known as traveling, and standing waves. The first phenomenon and the most simple and straightforward phenomenon we'll be focusing on in this video is reflection, a phenomenon which is observed very commonly in everyday life. Essentially, for something to reflect, the surface which is able to reflect the wave requires a smooth surface. A lot of the time when we are talking about reflection, we are very focused on the reflection of light. However, mechanical waves such as sound are just as easily able to reflect off a surface as well. In general terms, when something is being reflected, we have the wave energy coming in towards a surface, it then bounces off, changing direction. The wave energy coming in is known as the incident wave, and the wave energy being reflected off, fittingly, is known as the reflected wave. And we are able to measure the angles of these waves by measuring an incident wave angle and a reflected wave angle, sometimes denoted as theta I and theta R. When we measure these angles, we are looking at the angle between the wave and the normal to the surface. Remembering that if we are talking about a normal in any scenario for physics, we're talking about this imaginary line that exists perpendicular to a particular surface. In this case, we're looking at an imaginary line perpendicular to the smooth surface which is reflecting. What that means here in this scenario is that we have a right angle on either side of the normal. There is a general rule that we can follow when we are looking at reflection, and that is theta I is equal to theta R. In other words, the incident angle is equal in size to the reflected angle. We won't find this in the data sheet, but it is a very simple and straightforward rule to know and remember, also to apply. What becomes interesting though is not all surfaces are particularly good at reflecting. A general simple rule is that the smoother a surface is, the more effective it is at reflecting, and in the case of light, when it's reflecting, that would then result in a really clear picture. And this kind of concept can be seen in this first diagram which we have here. Because the surface is smooth, all incoming light is reflected off at the same angle. However, if we have a surface which is really rough, the reflections of light will go in all directions, scattering the light all around. And this is because in both instances, the law of reflection, angle I is equal to angle R, is actually being obeyed here. But because the incident angle changes in every scenario, the reflected angle changes as a result. To put that into context a little bit, I'm going to take a snapshot of two of these reflection scenarios over here. In the first scenario that I'm going to pull out, what we can see here is that the surface is roughly on an angle like this. We then have our light coming in. However, the normal is going to look something like this. It doesn't point directly straight up. It is off on an angle, resulting in a reflected angle that looks something like this. In contrast, if I look at the third reflection that's happening as we go from left to right, we can see that the resulting reflection is quite different. That is because the surface in this scenario is not parallel to the first. The surface looks something like this. So in this scenario, if we have an incident wave coming in at roughly the same angle here, our normal is going to be pointing in a completely different direction. And what that's going to mean is that the reflecting angle is going to be different as a result. In certain scenarios, this can be taken advantage of, particularly when we have really smooth surfaces which are able to still reflect light fantastically well. But if we have that surface overall be curved in shape, we can change the way in which all of that incident wave energy can be reflected. In the example of a concave curved reflective shape, what this will lead to is all reflected waves being focused into a single point. We then have a point of crossover, and they do diverge and split from there, but we end up with what we call here a focal point, a spot in which all of the reflected wave energy actually converges or meets. The opposite of this phenomenon is to have a convex shaped surface. So the curve essentially is going in the opposite direction. And what this will do is scatter the light out into all different directions. We call this a diverging mirror. Now, both of these different shaped reflective surfaces have their own applications, and this is something that we'll discuss in a little bit more detail in class. The next phenomenon that I want to look at today is refraction, essentially looking at what happens to waves as they move from one medium to another. It's really important to identify first that waves can speed up or slow down when moving between different mediums. As a general rule, waves slow down when they go into a denser medium and speed up when they go into a less dense medium. Something else to note that's really important is that when we do have a medium change, the frequency should remain constant. So if we have v equals f lambda, the velocity of a wave is equal to its frequency times its wavelength, what we can assume is that if f remains constant, but v either increases or decreases depending on what medium it's moving into, that wavelength will be the thing that adjusts to accommodate for the change in velocity. So given the structure of the v equals f lambda equation, what we can assume is that if we were to increase the velocity of the wave, this would result in an increase of wavelength in turn, and that if the velocity was to decrease, then the wavelength would decrease in turn as well, ensuring that both sides of the equation remain equal to each other. So let's just do a couple of quick practice questions to demonstrate this concept a little bit further. Here we have sound waves from a source vibrating at 680 hertz, traveling through the air at 340 meters per second. We're first asked to calculate the wavelength of these sound waves, and then to look at what would happen to the wave if it entered cooler air, which then made it slow. We're then asked to calculate what the new wavelength of the sound would be if we were to transition from the warmer air to the cooler air, which as a result slows it. So question one first. We have v is equal to f lambda. We're being asked to calculate for the wavelength, so let's rearrange for that. We can then substitute our values in, and our final answer here should be 0.50 meters, and that's correct to two significant figures. However, again, in question 2, this wavelength will change, not because of a change in frequency, but because of a change in velocity as we move into air of different temperature, thus different intensity. So again, we're calculating for wavelength here. We just need to substitute in our new values. This should give us an answer of 0.47 meters. In other words, we have a 3 centimeter difference here in wavelength as the sound travels through air of different temperatures and density. So refraction isn't exactly referring to the change in speed of waves as it moves through different mediums. Instead, it's actually the observed change in direction of a wave that we refer to as refraction. This phenomenon occurs because there is a velocity change, but the result that we see, that what we observe, is again that change in direction of the wave. So maybe you've seen before a clear prism can bend light, not only just bend it, but also split white light into its different colors. This is due to refraction and the fact that different colored light within the white light bends by different amounts. And if you line everything up sort of in those Goldilocks conditions, you will end up seeing some sort of rainbow form. Maybe you've done an experiment with a prism not to split the light, so to speak, but to cause a very distinct angle change in the ray. And then we can see as well here, something that's observed is that the direction of the light ray through the air and not through the perspex is actually parallel to each other. So we have a direction change as we go into our perspex medium, and then another direction change to recorrect and have it traveling in its original direction. This is not a coincidence. There's mathematical explanations for all of that and things that we'll unpack as we go further through with this unit. From a very everyday perspective, you may have observed objects look either closer, larger, change in shape and size in some sort of way. When you are looking at an object through a non-air medium, most common example being when you're looking at an object through water. And this again is a result of refraction and the changing of how we perceive light because it's changing directions and angles as it moves through different mediums. So we've noted that a change in velocity will lead to a change in direction. And that's something that can be observed in these two diagrams here. These horizontal lines here are supposed to show areas of compression in a sound wave. And what we can see here is that one, there is a distinct wavelength change as we move from the warm air to the cool air. That's to be expected, something that we showed in our calculations a second ago. But also that we have this direction change, that angle 1 is different to angle 2. But it's not something that we observe if the incoming wave is perpendicular to the barrier of our mediums. Effectively, in any scenario where we are looking at refraction, there are a few things that we're concerned with. First, the incident wave, the refracted wave and the direction that it's going in, as well as another normal line which we draw perpendicular to our two mediums. We're then looking for the angle of incidence and the angle of refraction. If refraction's occurring, the refracted angle should either be larger or smaller, depending on what mediums we're transitioning in between. There are some mathematical relationships which are included in our data sheet. These equations are going to be unpacked in later inquiry questions. So something to note is that when we move from less dense to denser, we should see a refraction that pulls the wave energy in towards the normal, closer to the normal, therefore decreasing the angle. If we're moving from denser to less dense, we should see that our wave moves away from our normal and thus increasing the angle of refraction. When imagining the behavior of these waves as we move between different mediums, I like to use the car in the mud analogy. General idea is that if a car on a road is approaching mud, which is denser and essentially slows the car down, if this wheel here is going to enter the mud before this wheel, that's going to make the car sort of turn and pivot in the way that it does here. In other words, the car is now traveling in a direction which is more closer to the normal. And then when we exit, that's going to allow the car to travel faster. And again, this wheel is going to exit the mud first, which is going to pull the car around and return it back to its original direction. A phenomenon which is very closely related to refraction is this concept of total internal reflection. In scenarios where we have energy moving from denser to less dense, as we observed before, the refracted ray is always going to be moving further and further and further away from the normal. In other words, the refracted angle is going to continue to get larger. This is something that's really well observed here in this diagram. We can see here that as we increase our incident angle as we go along, the refracted angle begins to increase as well, and it increases at a faster rate than the incident angle does. What that means is eventually we're going to hit this point of a critical angle where refraction is causing the wave energy to now move parallel to the barrier between the two mediums. At this point, we've begun this process of total internal reflection. What you can actually end up having is the incident wave not only moving parallel to, again, the interface between the two mediums, but if you continue to increase the incident angle, what you end up with eventually is the wave no longer refracting out into the less dense medium, but instead reflecting back into the denser medium itself. This again has a lot of applications. Some really important technologies are actually based off this concept of total internal reflection. It's something that we're going to be covering in more detail in class. The next concept that I want to introduce to you today is the concept of diffraction. Essentially, what diffraction talks about is the idea that waves can propagate outward when it moves past an opening, slit, or barrier. This explains why we can hear music playing in another part of the house. So when waves diffract, they're able to pass through a barrier of some description. There could either be two barriers on either side where there's a differing gap that the waves can go through. There may just be one barrier that the wave can sort of work around. But essentially, once the wave is past that barrier, the wave energy will again be able to spread out in all directions. So you can't just kind of chop a wave off at the sides and then just funnel it into a straight direction. Once it gets past its barrier, it's then able to, again, spread out like it wanted to do originally when it was being emitted from the source. The last big phenomenon that I want to talk about today is wave superposition, and the idea that two or more waves are able to interfere with each other, resulting in a new combined wave. So this key concept here, waves which overlap over the top of each other will combine to form a new wave, is being observed in this diagram here. We start with two separate waves, this blue wave and green wave. And because they're overlapped over the top of each other, they interfere with each other constructively. In other words, when we're looking at this interference, what we're doing is adding up the amplitudes of each of the waves at every single point along the wave. So for example, at this point here, because the amplitude of both the green and the blue wave is zero, they add up to 0. And thus the red wave, the resulting wave, is at this 0 point here as well. However, when we look at these crests that are all lined up nice and neat, the sum of the blue and green wave, which are both about, say, 1, according to this scale, assuming that this is 1, they add up to make 2, which is exactly where a resulting red wave is here. And on the flip side, we can add these two waves together when they're both -1, resulting in a wave that has this trough here of -2. We call this kind of interference constructive interference because both the green and the blue wave are building on each other. They're making or amplifying their wave. On the flip side, we can have destructive interference, and this occurs when the two waves are no longer lined up with each other. They're actually sort of working against each other. They're working the opposite to each other. So in this scenario, we have the blue and the green wave equal in displacement at any point. Say these amplitudes here again are both 1. However, they are the opposite to each other. One is +1 and one is -1. And when you add both of those waves together, that's going to result in 0. And what this means is actually if you have perfectly destructive interference which diminishes the wave, you end up with essentially no wave at all. We can observe this in sound waves, and when there's no wave at all, we end up with silence. And in the case of light waves, if we have destructive interference for light and there's no wave, we actually remove all light entirely and end up creating darkness, something that we will explore in more depth in our lessons. However, superposition doesn't always just occur by completely amplifying, complete constructive, or completely diminishing, complete destructive interference. A lot of the time, there might be some combination of both. So here we have our red and green wave going again, but in this case, we have them sort of overlapping over the top of each other in different ways at different points. At some point in this example, there is some constructive interference, say at this point. However, in this section, there is some destructive interference where both waves are actually working against each other, resulting in a smaller amplitude or smaller displacement in the wave. The final thing that we're going to be looking at today, beyond just our focus on what waves do, is distinguishing between progressive or traveling as well as standing waves. So first off, progressing or traveling waves propagate wave energy away from a source, and essentially those waves will just continue on and on and on forever and ever. So something to think about maybe there is what we generally think about in terms of sound. If I was standing on top of a hill and I yelled as loud as I can and you could hear me on another hill close by, what we would say is that the wave, the sound wave, is progressing or traveling as it goes from one point to another and continues on beyond that point as well. In contrast to that, though, we also have standing waves, and these are the results of a propagated wave being superimposed upon itself by an earlier wave which has been reflected back towards the wave source. So in this situation, what we have is a scenario like we can see in this animation here, where a wave is going towards an endpoint and then being reflected back. The way that that reflection happens can be different as to whether or not there's fixed or non-fixed reflection if we're talking about a physical wave. Those details we might talk about a little bit more in actual lesson time. The general concept here is that if you do have a wave which is reflected back towards the original wave source, this should be able to go and interfere with any further waves which are being made. That's not something that's being shown directly here in this animation, but if we were to continue making waves on this side, we then have a wave bouncing back, it's then interacting with the wave coming in. That's going to cause some superimposing waves, which look something like this. Maybe it could be destructive and it diminishes the wave. Maybe it could be constructive and it builds on the wave. And what you would end up with is on the wave, areas that are a node, essentially areas which stay completely still, and then areas where the full amplitude is being seen. We have an antinode where essentially that matter is going to be oscillating up and down. And then between these antinodes and nodes, there'll be areas where there is a smaller amount of oscillation that won't go all the way up to that maximum amplitude. So this gives us a little bit more of a visual of what a standing wave generally looks like. Again, we have these nodes, areas of the wave that don't oscillate at all. And then we have our antinodes, areas where we have a full oscillation that goes to the full extent of the amplitude of the wave, and then bits in between where there is a smaller oscillation occurring. And this is caused by, again, two waves which are interfering with each other. If we look at this blue wave, which is propagating from left to right, let's say that this is the wave that is being generated, and that the red wave going from right to left is the wave that is being reflected back. What we have is different amounts of superposition at different times, and as they overlap, that's resulting in either constructive interference, where we get our really, really big peaks and troughs, or destructive interference, where the peaks and troughs of both waves are completely opposite to each other, resulting in a completely, essentially flat line for our wave, complete destructive interference. Here I have some different videos which actually demonstrate and show standing waves in a lot more detail. They're going to be in the description. I highly recommend you spend some time having a look over those. We're also going to be looking at making some standing waves in class. You've actually already made some standing waves in your other experimentation that you have done, but we'll do some more. And then as well, this website here has several GIFs about waves and different wave behaviors and different wave phenomenon, things that we've covered already, things that we're going to continue covering. I'll put that in the description of this video as well. Always a good link to be looking at with a bunch of different animations. Thank you very much. In the next video, we're going to be focusing on the concept of resonance. But until then, have a good one.